So, to calculate the moment of inertia of real-world object, which is usually irregular, this is one of the method we can use. So this is the equation. Let's take a look at each component of it. So Ixx is basically the moment of inertia we want to know. So it's moment of inertia about axis of rotation. And the unit will be kilogram times meter squared, because we know the moment of inertia will be mr squared, right? So mass times distance squared. And how about m? We'll just like ignore this disgusting thing first. So m will be the mass of the object. So that's still pretty simple. G will be acceleration due to gravity, which is usually 9.8. And L will be the distance from axis of rotation to center of mass. Right? And how about this thing? T divided by 2 pi squared. T will be time period required for one complete swing. What does that mean? So this is the method we're going to use to get the moment of inertia in real world. So this method is about to swing the object you want to calculate its moment of inertia. So for example, we have a baseball bat here. We fix one end on the axis of rotation. So here is the axis of rotation. And we release the baseball bat from here. It's gonna swing, right? So it's going to swing here, like the second picture, and then swing back to the original position. So this is a complete swing. You go to the other end and go back to your initial position. That's one complete swing. And the time period required for one complete swing will be t. So, to calculate the moment of inertia of this baseball bat around the axis of rotation, you're gonna swing it, you're gonna fix it and swing it and plug the time for one complete swing here, divide by 2 pi squared, plus the mass of the baseball bat, gravity, which is 9.8, and L, which is the length, the distance from center of mass to the axis of rotation. So that would be probably this distance. Yeah, so that's how you use the equation. So basically, we're gonna get the mass of this object, the distance between axis of rotation to center of mass, and also to observe the time of one complete swing. Plug into the equation, you got a moment of inertia. So that's the equation we're gonna use. And think about it. Do you think in these two situations, like in the first one, the axis of rotation is at the grip of this baseball bat. At this one, the axis of rotation is at the head of the baseball bat. Do you think the moment of inertia would be the same between these two situations? You can think from like moment of inertia is related to angular mass, right? Which usually reflects how hard it is to move the object. So do you think that that'll be easier to swing in one of the situation, or that'll be equally easy? Like intuitively that'll be different, right? I would assume that'll be easier to swing from this end. So actually the moment of inertia will change if you change the axis of rotation. So that's what we're gonna figure out today. We have two objects. One is a baseball bat. The other is a racket. And we're going to hang the object on the wall on different ends and to calculate the moment of inertia, to compare if that's different. Okay, that's what we want for exercise 1. So here will be 2 tables you need to complete for exercise 1. And because this is a virtual lab, so I've collected most of the data for you. So the acceleration due to gravity will be 9.8. And we actually have 10 complete oscillations and get a total time for the oscillation. So you can get an average time for one oscillation. That'll decrease the error, because if you want to just get the time for one complete swing, that'll be like not that accurate. So we got 10 complete swings and the total time. So you gotta divide 16.26 divided by 10. That's how you got the average time for one oscillation. That is t, you want to plug in the equation. And also, you have L, which is center of mass to axis of rotation. So, for a baseball bat, the center of mass to the grip is 0.54 meters, and the center of mass to the head or to the other end would be 0.32. So actually L is different, which means the moment of inertia it should be different, right? Because you have different variables here. And also for tennis racket, it's the same, they have different L. And the mass will be the same in each object. So you just plug in 9.8 here, and you have the time, plug in this column, and plug into the equation to get the Ixx. And it should be different from different ends in the same object. So, and that represents how easy or how hard it is to rotate the object from that axis of rotation. So that is all about exercise 1, and we'll talk about exercise 2 later.